Picture a room full of engineers at Nvidia's headquarters in Santa Clara, California. It's early 2025. Their H100 chip, the most powerful AI accelerator on the planet, is sold out. There's a waiting list. Governments are offering billions for access to it. Tech companies are restructuring their entire roadmaps around who can get enough of them. That chip, the H100, had taken Nvidia 5 years and the world's most advanced semiconductor factories to build. It runs on TSMC's cutting-edge 4nm process. It costs between $30,000 and $40,000 per unit. And for 2 straight years, nothing on Earth came close to touching it. Then China released a number. Not a prototype, not a press release. A benchmark. A real-world test result. Run by DeepSeek, one of the most credible AI labs in China, showing that Huawei's Ascend 9110C chip, manufactured on older technology, inside China without TSMC, without UV lithography equipment, had reached roughly 80% of the H100's inference performance. 80%. And that was just the chip by itself. What they built around it was something entirely different. Something that, by some measures, has already surpassed Nvidia's most advanced system on the planet. This is the story of how that happened, and why the people who run America's technology industry can no longer afford to look away. There has been a rule in the semiconductor industry for as long as most engineers can remember. It goes like this. To build the best chips, you need the best tools. And the best tools only go to the West. That was the wall. The assumption built into every US export control policy was straightforward. If you deny China access to the machinery, you deny China access to advanced chips. No EUV machines, no sub-7 nanometer processes. No sub-7 nanometer process, no competitive AI hardware. No competitive AI hardware, no AI race. It was a logical chain. Clean, defensible, and reassuring. The problem is that China didn't try to break that chain. They simply walked around it. Huawei's engineers at HiSilicon, the semiconductor design arm that Huawei built quietly over 2 decades, started with what they had. SMIC's 7nm deep ultraviolet process. Older machines. Lower yields. And instead of waiting for access to tools the United States refused to provide, they redesigned the architecture of the chip itself, and then redesigned the system the chips lived in. If you've been following China's technology story and find what's happening in semiconductors as important as we do, consider subscribing, because what comes next in this series is going to reshape how you think about the global AI race. The rule, it turns out, wasn't unbreakable. It just hadn't been tested hard enough yet. To understand why what Huawei did is genuinely remarkable, you need to understand the problem they were actually solving. And it is not the problem most people think it is. The obvious problem is the manufacturing node. When we talk about 7nm versus 4nm chips, we're talking about transistor size. The smaller the transistor, the more you can fit on a chip, and the more you can fit. The more raw computing power you get from the same piece of silicon. Nvidia's H100 is built on a 4nm node. Huawei's Ascend 910C is built on a 7nm node. That gap represents roughly 2 full generations of semiconductor manufacturing progress. In raw transistor terms, that's not a small difference. A 4nm chip can pack nearly twice as many transistors into the same surface area as a 7nm chip. Twice the transistors means faster switching, lower power consumption, and in most cases, significantly higher performance per watt. So the question engineers were asking, the question a lot of American analysts were counting on, was simple. How could you possibly make a competitive AI chip on a 7nm process when your competitor is 2 full generations ahead? The answer starts with understanding what actually limits a chip's performance in AI workloads. Unlike a traditional CPU, where a single thread of computation runs as fast as possible, AI hardware is almost entirely about parallelism, running thousands of smaller calculations simultaneously. The bottleneck is not clock speed. It is memory bandwidth. It is how fast data can move between the processor and the memory it needs to operate on. And it is the ability to keep all those parallel compute cores fed with information fast enough that none of them sit idle. This is why Nvidia's CUDA software ecosystem built over 17 years has been their real moat, not just their hardware. CUDA tells Nvidia GPUs how to schedule those thousands of parallel tasks efficiently. It manages memory. It handles precision. Without CUDA, a chip with extraordinary raw performance becomes significantly less useful in practice. That software dependency is exactly what trapped China for nearly a decade. Every AI researcher in the world learned to write code in CUDA. Every AI framework PyTorch, TensorFlow, JAX runs best on CUDA native hardware. When Chinese companies tried to use domestic chips, they faced a brutal reality. The hardware might work on paper, but the software ecosystem simply wasn't there. Models ran slower. Bugs were harder to trace. Engineers defaulted back to Nvidia hardware because the path of least resistance led straight to Santa Clara. This is the wall that the export controls were really defending. Not the hardware. The software gravity well that Nvidia had spent 2 decades building. Huawei understood this, and they made a decision that most people in the industry underestimated. Instead of trying to compete chip for chip on raw specifications, they would build a system architecture that compensated for the per-chip performance gap, while simultaneously building their own software stack called CAN, or Compute Architecture for Neural Networks, from the ground up. It was a slower path, a harder path, a path that required not just engineering resources, but the kind of patient, decade-long institutional commitment that very few technology companies in any country have demonstrated. But here is what makes 2024 and 2025 different from every year before them. For the first time, that patient commitment started producing results that outside observers couldn't explain away. Let's get specific, because this is where the story becomes important. The Huawei Ascend 910C, released into volume production in the second half of 2024, is not a single chip in the traditional sense. It is 2 Ascend 910B processors combined on a single board using an architecture called multi-chip module design. Huawei's Silicon engineers took 2 processors and connected them using a proprietary interconnect that allows them to function as a unified computing unit. The result? 800 T-flops of FP16 compute performance. That's 800 trillion floating point operations per second at half precision, the standard measurement for AI training workloads. For context, Nvidia's H100 delivers approximately 989 TFLOPS at FP16. So the 910C, on a single chip comparison, comes in at roughly 80% of the H100's raw compute performance. The memory configuration is equally important. The 910C carries 96 gigabytes of HBM2E memory, high bandwidth memory, with a bandwidth of 3.2 terabytes per second. That bandwidth figure is significant. It is lower than the H100's 3.35 terabytes per second bandwidth, but not dramatically so. And for inference workloads running a model to generate answers, as opposed to training it from scratch, inference performance is heavily tied to memory bandwidth, not just raw compute. In April 2025, DeepSeek, the Chinese AI lab whose R1 model sent shockwaves through Silicon Valley when it launched in January of that year, published a formal assessment of the Ascend 910C for inference tasks. Their conclusion: the 910C delivers approximately 60% of H100 inference performance on a chip-for-chip basis. That number is lower than the raw T-flops comparison suggests, and it reflects the real-world inefficiencies of using a software stack Huawei's can that is less mature than Nvidia's CUDA. 60% is not parity, but it is close enough to matter commercially. And Barclays, the investment bank, published an estimate in 2025 projecting that by 2026, 70% of all AI compute demand globally would come from inference rather than training. Which means Huawei's can that matters most going forward is exactly the one where the 910C is most competitive. But the story doesn't end with the chip. It ends with what Huawei built around the chip. In April 2025, at the World Artificial Intelligence Conference in Shanghai, Huawei unveiled the CloudMatrix 384. The name refers to its configuration: 384 Ascend 920C accelerators interconnected through what Huawei calls an all-to-all supernode topology using their proprietary unified bus, or UB network. The CloudMatrix 384 is not a chip, it is a system. And it is designed to do something specific: compete at the system level, not the chip level. To understand what this means, you have to go back to October 2022. That month, the Biden administration enacted what many analysts called the most sweeping set of technology export controls in American history. The rules targeted AI chips specifically. Nvidia's A100, its flagship training chip at the time, was immediately banned from sale to China. Within weeks, Nvidia had designed a workaround chip called the A800. Slightly downgraded to fall just below the export thresholds. And the message from Washington was consistent: we will use semiconductor access as a strategic tool to prevent China from developing competitive AI capabilities. The policy was built on a real insight that chips are the critical infrastructure of the AI age. But the policy had an assumption buried inside it that turned out to be fragile. It assumed that China would remain a consumer of Western semiconductor technology rather than becoming a producer of its own. And it underestimated the degree to which the export controls themselves would accelerate China's investment in domestic alternatives. When Nvidia's chips became unavailable, Chinese tech companies had two choices: slow down their AI development or find another way. Companies like Alibaba, Tencent, ByteDance, and Baidu all turned to Huawei. The Chinese government accelerated subsidies. State-backed procurement contracts guaranteed demand. And Huawei, already years into building its Ascend chip line, suddenly had every incentive and every resource it needed to scale as fast as possible. The export controls did not stop China from developing AI chips. What they did arguably was ensure that China would build an entirely padded, arguably Wasco system, one that is now, in 2026, beginning to mature. The reaction from outside China tells you as much about the stakes as the technology itself does. In the United States, Nvidia's response has been to accelerate its own roadmap while simultaneously lobbying for a different approach to export controls. Jensen Huang has argued publicly that restricting chip sales to China does not slow Chinese AI development, it only costs American companies revenue and pushes Chinese firms toward domestic alternatives faster. Whether or not you agree with that position, the fact that Nvidia's CEO is making it at all tells you something about how the industry views the effectiveness of the current policy. The United States government, for its part, has responded with more controls. The Trump administration's approach in 2025 and 2026 has been to maintain and in some cases tighten the export restrictions while simultaneously restarting limited Nvidia chip sales to China under specific licensing agreements, a dual-track policy that, according to analysts, satisfies neither side of the debate. The global AI hardware market is bifurcating. There is no longer a single supply chain. There is a Western supply chain centered on Nvidia and TSMC. And there is now an emerging Chinese supply chain centered on Huawei, SMIC, and a growing constellation of domestic chip companies. Countries that want to build AI infrastructure are increasingly being asked which side of that divide they intend to stand on. Here is where this story stops being about technology and starts being about the world most Americans will be living in over the next decade. Artificial intelligence is not a product. It is infrastructure. The same way electricity rewired every industry in the 20th century, AI is in the process of rewiring every industry in the 21st. Healthcare, logistics, finance, manufacturing, defense, every sector is being reorganized around who has the best AI and who has the most of it. And AI hardware chips is the foundation that everything else rests on. When China's Huawei ships 6 million AI chip dies in a single year, and when Chinese AI labs begin running their frontier models on domestic hardware, what that means practically is this. China's AI development timeline is no longer constrained by American export policy. The assumption that Western technological controls could slow China's AI capabilities by 5 years or 10 years is being revised in real time. For American workers in the semiconductor industry, this is a direct competitive threat. The United States currently produces roughly 12% of the world's semiconductor supply, down from 37% in 1990. TSMC is building fabs in Arizona, Intel is restructuring its foundry business, and the CHIPS Act allocated roughly $52 billion to bring advanced manufacturing back to American soil. But those investments take years, and the competitive window is not staying open indefinitely. For American consumers, the implications are more indirect but real. If Nvidia faces a genuine competitor not just in China but globally, as Huawei expands its reach into emerging markets, the pricing power that has kept H100 chips at $30,000 to $40,000 per unit may eventually erode. Competition typically drives prices down, and cheaper AI compute in the long run means cheaper AI services for everyone. For the broader question of military and strategic competition, the implications are the ones that keep national security analysts awake at night. AI capabilities are increasingly tied to defense systems, from logistics and targeting to cybersecurity and signals intelligence. A China that has closed the gap in AI hardware is a China that is closing the gap in the underlying infrastructure of modern military capability. None of that is a prediction about what will happen. It is a description of what is already happening, in real time, visible to anyone willing to look at the data without wishful thinking filtering the view. This story would not be honest without acknowledging the genuine limits that Huawei and China's semiconductor industry still face. And those limits are real. The most fundamental constraint is manufacturing. Huawei's Ascend chips are built on SMIC's 7nm deep ultraviolet process. That process has a yield rate, the percentage of chips that come out of the factory, working correctly estimated by Mizuho Securities at around 30%. For comparison, TSMC's yield rates on its advanced nodes are believed to be substantially higher. A 30% yield means that for every 3 chips Huawei starts manufacturing, 2 are discarded. That drives up cost, limits the total volume Huawei can ship, and makes the economics of scaling difficult. Power efficiency is the second major limitation. The CloudMatrix 384 system, for all its system-level compute performance advantages, draws approximately 560 kilowatts of power at full load. Nvidia's GB200 NVL72 draws 145 kilowatts. The Huawei system is 3 times less power efficient per flop. For Chinese data centers operating with government energy subsidies, that trade-off may be commercially manageable. For any company outside China buying Huawei systems and paying market electricity rates, that power premium is a significant economic barrier. Memory is the third constraint. HBM high bandwidth memory is currently produced almost entirely by SK Hynix, Samsung, and Micron, all of which operate under export control frameworks. China is investing in domestic HBM production, but the technology is years behind the global leaders. Without a reliable domestic HBM supply, Huawei's ability to scale its most advanced systems remains partially dependent on memory components it cannot fully control. These are not minor footnotes. They are structural constraints that will take years to overcome if they can be overcome at all at current manufacturing maturity levels. The gap has narrowed. It has not closed. There is a sentence that keeps appearing in semiconductor research reports, in analyst briefings, in the private conversations of people who build and fund AI hardware for a living. The sentence goes like this: we assumed the node was the moat. The node, the manufacturing process, the transistor size. The assumption that sub-4 nanometer fabrication was an unassailable technical barrier that without TSMC, without UV, without the supply chains that took 60 years to build across Japan, the Netherlands, and the United States, a competitor simply could not reach the frontier. What Huawei's Ascend program has demonstrated, not conclusively, not completely, but undeniably, is that the node is not the only moat. System architecture is a moat. Software investment is a moat. Government-backed demand guarantees are a moat. The willingness to accept lower per-chip efficiency in exchange for raw system-level scale is a strategy, not a failure. We are watching the semiconductor industry bifurcate in real time. Two supply chains, two software ecosystems, two roadmaps running in parallel, diverging further with every year that passes. The world's AI infrastructure is splitting at the hardware level in ways that will shape geopolitics, military capability, economic competition, and everyday life for a generation. The H100 is not obsolete. Not today. But the world in which it was the only option worth considering, that world is already gone. The question is no longer whether China can build competitive AI chips. The question is how competitive they become, and how fast, and what that means for a global technology order that was built on the assumption that only one side of the Pacific could answer that question. If this video changed how you understand the AI chip race, hit subscribe and turn on notifications. We cover stories like this every week, with the same depth and the same commitment to getting the numbers right instead of just getting them out fast. And for the comments, I want to ask you something specific. Do you think US export controls on AI chips have actually slowed China's development? Or have they accelerated it by forcing Huawei to build domestic alternatives? Drop your answer below. I read every one.